Okay, so I'll solve a few problems on limits to demonstrate different techniques we have. Okay, we have three or four techniques. So let's say review of limits. So we talked about the theory of this a lot. So let me immediately start with the problems. One problem is, okay, so find limit as xy goes to 0, 0 of xy over x to the 4 plus y to the 4. Okay, so when you look at something like this, the first feeling should be the numerator is quadratic, the denominator is quartic, so the denominator goes to 0 faster, making this probably go to infinity. Okay, this may be wrong, but first you must have a feeling. Okay, so our feeling is this, so we attempt to show that the limit does not exist. There are several ways, well, two ways to show this. In this case, I'll use one path. Okay, so here we say, consider, well, if this limit exists, then all restricted limits will be the same. So if you find one limit which is bad, the limit does not exist. Okay, consider the path y equals x. Okay, so we look at the limit as its y goes to 0, 0, but we restrict it to the path y equals x of xy, x to the 4 plus y to the 4. Now this becomes x goes to 0, and this is now x squared. This is 2 times x to the 4. Okay, so you cancel this, limit x goes to 0. Remember that we were talking about punctured disk, so this is the reason why we do that. X is never 0, so we can cancel this. We have 1 over 2x squared, and this limit is equal to infinity. Technically speaking, the limit does not exist. Okay, so this thing we called one-path test. This is not a standard name, but we call it one-path test. So again, if the limit exists, it is going to be the same along any path. In particular, for the terminology of one-path test, if the limit exists, then it will exist along every path. So we found a path along which the limit does not exist. So the general limit does not exist. Okay, so this is one technique we do. Then we have the two-path test. So let's look at this. We look at limit xy goes to 0, 0 of x to the 4y, x to the 8 plus y squared. Okay, so again, here we suspect that the limit does not exist, but we will use this example to demonstrate two-path test. Here, if you first try the path y equals lambda x. Okay, so you will see the following. Okay, so let me now omit this thing. So x to the 4y, x to the 8 plus y squared. When I restrict it to y equals lambda x. So what do I find? I find lambda x to the 5 over x to the 8 plus lambda square x squared. So I cancel x squares. I have x cubed lambda over x6 plus lambda square. Okay, so this goes to 0 as x goes to 0. So if you are approaching the origin along any line, you get 0. So we know that this doesn't give us any information. Okay, the necessary condition for the limit to be equal 0 is satisfied, but the sufficient condition is not satisfied. Okay, try the path y equals lambda x squared. So we will again have something like this, x for y over x to the 8 plus y squared. Restrict this to y equals lambda x squared. So you have lambda x to the 6 over, okay, I put this x to the 6, x8 plus lambda square x to the 4. Okay, so I'll again cancel this. I'll have lambda x square over x to the 8 plus, I canceled something here. Let me see. Okay. What did I cancel? I canceled x to the 4, so I have x to the 4 here. Okay, plus lambda square. Okay, so this again goes to 0 as x goes to 0. Okay, so now I'll have to take my sweater because we were expecting this room to be cold. Okay, so let me see, where are we? Okay, let's try again y cube. So did I do this correctly? You are not responding anything, and then we are having something wrong here. Okay, so I put x squared here. This was x to the 4, x6. Okay, so here x4. Okay, I have this. So let us now put y equals lambda x cube. Okay. So this should, then again I'll write the same thing, x to the 4y over x8 plus y squared restricted to y equals lambda x cube. Okay, so I have x to the 7 now, and I have lambda here. I have x to the 8 plus lambda square x to the 6. So you see that this is again x lambda over x square plus lambda square. So this again goes to 0 as x goes to 0. Okay. So we found 3 families of paths along which the limit is 0. Okay, so I'm doing this to train our feelings that we don't jump to the conclusion that the limit is 0. Okay. Next, finally, in this case, as you are expecting, now put y equals lambda x to the 4. So this thing, x to the 8 plus y squared restricted to this path, lambda x to the 4 should be lambda x to the 8 over x to the 8 plus lambda square x to the 8. Now this is equal to lambda over 1 plus lambda square. So this goes to this number as x goes to 0. Okay? The limit depends on path. So the limit does not exist. By the two-path test. Okay, so this name is now standard. Okay, so two-path test is used to find 2 different paths along which you get 2 different limits. Okay, then the limit does not exist. Of course, we could also do this by, you see, 4 over 8 plus 1 over 2 is equal to 1. If it is 1, the limit does not exist. Okay, but I did this to demonstrate some aspect of the limits. Okay, you can find different limits along which all the limits are the same. Still, that doesn't tell us anything. Okay, it tells us that if the limit existed, it would be 0, but the limit does not exist. Okay, so the other one is we didn't mention, but sometimes it is useful, but you should use it very carefully, putting in polar coordinates. Okay, the other problem. I'll do this. Okay, we have x So again, the problem is limit x, y goes to 0, 0. I have, what is this? X squared y cubed over x squared plus y squared squared. Okay? So when you have x squared plus y squared, then obviously a circle comes to mind. So sometimes you can do this. Okay, so put x equals r cos theta, y equals r sine theta. Here x, y goes to 0, 0 is equivalent to r goes to 0 and theta is free. Okay, so it is this part that makes this complicated in some problems, but sometimes if you can get rid of theta, this is easy. You see, x squared plus y squared is such a setup. So this is limit r goes to 0. So this is r to the 5 cosine squared theta sine cube theta divided by, this is r squared, r to the 4. Okay, so you cancel these r's. Since r is going to 0, it's not 0. Limit r goes to 0, and here you have r times something, cosine squared theta sine cube theta. Okay, now in this case it is easy. No matter what theta is, this is going to be a number between -1 and +1. Okay, you multiply it with r, that goes to 0, so the answer is 0. Okay, but sometimes we don't cancel thetas here. We also have thetas. If this thing is divided by some cosine theta, sine theta stuff, you should be very careful, because for some funny behavior of theta, the limit may not exist. You should be able to catch it. The thing that fools you here is you are tended to think that theta will be constant. Okay, so theta will not be constant, because you can say that for particular values of theta, the fraction or the expression in theta will be something acceptable, so r will kill it. But theta is also free here, so theta may jump up and down and make the denominator, if you have a denominator, make the denominator 0. Okay, then then you are in trouble. So you use this only when you are certain that thetas will cancel. You will be able to see what r is doing to the other things. Okay, so this is using polar coordinates, but we don't emphasize it because it's not good all the time. I'll do the same example with the squeeze theorem, because this is, you see, is good for squeeze theorem. So why don't I do it here? Okay, so the same problem with squeeze theorem. Okay, so we want to squeeze this between something. If we know that in such cases the denominator vanishes only at the origin. So if the limit exists in such rational functions, the limit will be 0. So 0 is less than or equal to the absolute value of this. Well, the absolute value will go only in y. So let's write this. Okay, let me write this x squared y cubed. We have x squared plus y squared squared. Okay, so this is first of all equal to x squared over x squared plus y squared. Then I have y squared over x squared plus y squared, and then I have y. Okay? So you see that this is less than or equal to 1. This is less than or equal to 1. So the whole thing is less than or equal to this. Okay? So let me remind ourselves that this is less than or equal to 1. This is less than or equal to 1. So now the squeeze theorem says that as xy goes to 0, this is constant. It doesn't look at anything. And as xy goes to 0, this goes to 0. Therefore, this thing goes to 0 as xy goes to 0, 0. So the limit is 0. So limit xy goes to 0, 0 of x squared y cubed over x squared plus y squared is 0. Okay? Okay, so somebody asked me a question last time. Most of these things, for example, here, you see we found that the limit depends on lambda. Okay, but you see this has a minimum and maximum. It's a bounded function because as lambda goes to infinity, this goes to 0. So it behaves between something. So if you find the maximum of this, probably the maximum is 1 over 2, okay, or something like this. So somebody asked me a question if we can find a rational function which doesn't have a limit at the origin, the limit depends on path, but it wraps to all of the z-axis. Okay, so we can find such a function. So now I'll give an example. Okay, so here is the example. So what is the number? I forgot the number now. Okay, so let's say 38. So people watching the video will wonder where the all 35 problems went. So problem 38, find limit xy goes to 0, 0, x cube y cube over x 36 plus y to the 4. Okay, now let's use this theorem, which I humorously call Serto's theorem. You have 3 over 36 plus 3 over 4. That's less than 1. Okay, so the limit does not exist. No problem. Okay, let's also think about the graph of this function. You see when x and y are larger than 1, okay, outside the unit disk, you are dividing something with the 36th power of x. Okay, it's a very huge number compared to x cube and y cube. So the graph of this is almost 0 as you move slightly away from the unit disk. So if you plot this on the computer will give you just a flat thing, and at the origin there is some pole. Okay? So the graph is very small, and when it is approaching to the origin, let's see what happens. So I do this, okay? Consider the path. So I'll use lambda here. Y equals lambda times x to the 11. Okay? Then let us look at this thing. X cube y cube divided by x 36 plus y 4 restricted to the path lambda x 11. Okay, so before we do the algebra, again let us visualize what this path is. You see this path is something like this. Okay, so this is x, this is y. Well, you see that it is symmetric with respect to the origin. So if the graph is, suppose lambda is positive, so the graph is here, and the same thing is here. So I'll just draw here. Suppose this is 1. At 1, x11 is 1, so you get only lambda. Okay, so suppose this is lambda is positive, so this part is 1 lambda. But if you are just to the left of this, you get a number less than 1. You are taking its 11th power, so it's very, very small. Okay, so the graph is, and if you are slightly above, if your x is slightly larger than 1, x to the 11 is very large. So the graph is coming like this and immediately goes like this. Okay, so this is the graph. But you see, it shouldn't fool you because given any point here, there is a lambda, very huge lambda, so that the graph passes from there. Okay, because then this 1 lambda will be huge up there, and coming from there, it will pass from here and come here. Okay, so we will be able to cover all directions here, depending on whether lambda is, in this case, when lambda is positive, this is what's happening. And when lambda is negative, then we'll have these parts. Okay, so all directions will be covered, but you have to use very, very large lambdas. Okay, so let's see, when we put this thing in here, we have x36, that's x36, and I have lambda cube. Here I have x36 plus This is 40 lambda 4x to the 44. Now I cancel x's, okay? X different than 0, so we are not looking at what's happening here. So this is lambda cube 1 plus lambda 4x 8. Okay? Now we take the limit as x goes to 0. This goes to lambda cube as x goes to 0. Okay? So given any real number, it has a unique real cube root. So you can cover every number by lambda cubes. Choosing lambda, with lambda cubes, you will get all of the z-axis. Okay? Okay, so since for any alpha in R, there is a unique lambda in R with lambda cube equals alpha, the graph of this function wraps around z-axis and touches it. So touches is in the limit at every point. Okay, so anything is possible. Okay, so and the other thing that we do is finger counting. So let's also do that as an example. So for example, we have, so this is an example of a two-path test, but we are demonstrating that the pathological behavior of the graph around the origin can be as wild as this one. Okay, so 48, let us look at limit as x, y, z goes to 0, 0, 0, and I have x, y, z square over x square plus y4 plus z6. Okay, so here we consider 1 over 2 plus 1 over 4 plus 2 over 3. I think I calculated this, so let me check this so that I don't make an error. So this is larger than 1. So the limit does not exist by Sartor's theorem. Okay, so let's make it like this, and let's put a smiling face there so we make clear that we are having fun. Okay, so, and sometimes I get this question, what happens this is 1? But it is clear that since we are saying that, so what did I say? So the limit is 0, 1. I don't know my own theorem. So the limit is 0 by, okay. So sometimes they ask me what happens if this is equal to 1, but the statement of this rule is that the limit exists if and only if this is strictly larger than 1. Okay, so if it is 1, it is not strictly larger than 1, so the limit does not exist. So here is an example. Okay, so 1078. Limit, again, x, y, z goes to 0, 0, 0. So here I chose these numbers so that this thing will be 1, x, z cube over x squared plus y 4 plus z 6. Okay, so here you see you have 1 over 2 plus 0 over 4 plus 3 over 6 equals 1. The limit does not exist. Okay, so, well, I once went to a seminar saying 1001 uses of vector bundles. That's one when we were grad student and we were trying to understand what this vector bundle stuff is, and it was just heaven. This guy will tell us 1001, so it's definite that I'll understand something. So he gave us only 3 examples, and as he said, I'll leave the rest as an exercise. So to fill in the missing problems is an exercise. Okay, so this is the application of main application of limits. So talking about the exam, in the exam you will not have direct questions like this, okay? So, but you may have something like this where you have to be creative, find a different path, or there may be some parameters here. In order for the limit to exist, what should the parameter be? Okay, so expect that kind of questions. Look at the past exams. And the tone of the course changes from year to year. So if you look at some exam questions in the past, it doesn't make much sense to you, skip it. It means that that year we concentrated on that concept, this year we are not. Okay, so now that is the end of this review. Now let's again go back to partial derivatives. I'll repeat the definition, and then again we'll look at different aspects of that. Partial derivatives. Okay, so we are talking about functions of several variables. There are several parameters in it. We fix all the parameters except one and take the derivative with respect to that. Okay, so this is a simple idea. It's a simple technique. What we want to do is it of any use? In one-dimensional case, it was very useful. You take the limit of you take the derivative of a function if it exists. For example, the function is continuous. You immediately know that. Okay. If the derivative exists, there is a tangent line to the function. The tangent line approximates the function analytically. Okay, so that's the important thing. If you calculate the function at several points, that's a different story. But if there are some parameters in the function, then, and if the function is complicated, you want to understand how the function behaves around the point, its tangent line gives you a quite a fair idea, and it's very easy to calculate the tangent line because it's a linear function. Okay, can we do the same thing here? So these are the questions that we are trying to understand. So first of all, how do we define partial derivatives? Okay, so let f x y be a function of two variables defined around a point x sub 0, y sub 0. Okay, so what happens here is the picture. Okay, so this is the x-axis, y-axis, and here we have our point. I'll try to write it like this. Okay, so the function is defined around there. So when I fix y, for example, okay, so let's use this. Suppose we fix y. Okay, that means we are looking at this one. So this is the point y sub 0. Any point here is of the form x, y sub 0. Okay, that's the line y sub 0. So fixing a point in here, fixing one of the parameters means that I restrict this function to this line. Now it becomes a function of x. Now I take its derivative. Okay, so that's the idea. Okay, so partial derivative of f x y at x sub 0 y sub 0 is, okay, sometimes we denote it like this. Partial derivative of f with respect to x evaluated at the point x sub 0 y sub 0. So we define it. Remember that this means that this symbol so far has no meaning, but from now on, every time I see this picture, I'll understand this. This is limit as x goes to x sub 0, f of x. I restricted this function here, so the second coordinate is y sub 0, minus I evaluate this now here. Okay, so it is x sub 0, y sub 0, x sub 0, y sub 0, divided by, as usual, the difference, x minus x sub 0, if the limit exists. Okay, if the limit exists. Because you see, we have lots of examples where the limit exists and the limit does not exist. So If the limit does not exist, we don't talk about the derivative. We say the derivative does not exist. Okay? And similarly, now I will talk about the limit in the other direction. So you restrict the function here. So this point is now x sub 0. A typical point, okay, this time let me put the typical point here. A typical point is x sub 0, y. So this point moves towards here. Okay. Similarly, partial derivative of f respect to y at the point x sub 0, y sub 0, if it is limit y goes to y sub 0. Okay, so this thing moves towards here. F of a typical point is of this form, minus I evaluate the function here, f x sub 0, y sub 0, divided by y minus y sub 0, so when the limit exists. Okay. So let's see. We have other notations for this. Okay, so okay, let's say sometimes we want this to be a typical point. Okay, so when we want x sub 0, y sub 0 to be a generic point, that is when we want to use x, y to denote it, then it's just a matter of notation. So we write it like this. Then derivative of f respect to x, it's a function of xy, is equal to limit, say delta x goes to 0. Okay, so you see that this part is delta x, delta y. So f of x plus delta xy minus f of xy divided by delta x. And similarly, the other one, delta f delta y at xy is equal to limit delta y goes to 0, f of x, y plus delta y minus f of xy divided by delta y. Okay, so this is just rewriting exactly the same thing, but this time we hope that we get a better notation. So now I can use this xy as a joker. I can put any numbers there. Okay, so other notations that are in use, used for partial derivatives. Okay, so first one is this, for example. The other one is we put an x here, okay, denoting that we are taking derivative with respect to x. So another one is we treat this as an operator. Okay, so sometimes we write this and we put the functions here. And sometimes, since we are seeing this as an operator, we say we are taking the derivative with respect to x of f. Here you can put xy. Okay, so I'm not doing this. So here, since I didn't put xy here, let me not put xy here. Okay, and sometimes when we have more than 2 or 3 variables, when you have up to 3 variables, x, y, z is okay. But when you have 5 variables, then x, y, z, w, what are you going to use after that? So you use as the names of the parameters x sub 1, x sub 2, etc. So you say, I'm taking derivative with respect to the first variable of f. Okay? So these are the notations that come to my mind. Most of the time, you understand in the context that the notation they are using refers to partial derivative. So you have the same similar thing for the derivative with respect to y. Okay, so I'll not repeat it. You just put y here, except that now y is the second variable, so you put 2 here. Okay, let's now draw a picture. Okay, so instead, let's delay the picture to the next hour. Let's have our quiz, because the quiz is about the limits. If I brought the correct quiz, so let me check. Okay, so the quiz is about finding limits here. So it's a good place to have the quiz here. Next hour, we just start without any break on the picture tangents, and we'll try to answer the question, if these partial derivatives exist, is the function continuous? That sort of thing. Okay, so as usual,